So today we have Magda. Magda is a visiting student with a Fulbright scholarship. So she has been working for us for how long? 2 years?
Yeah, something like that.
Something like that. Recently, she published a paper on the transactional speech and language processing, and today she will tell us about her research in the last year.
Thank you, Jesus. So today I am going to present some of our work on diarization, mainly end-to-end neural speaker diarization with non-autoregressive attractors. And this work has been recently published as a journal paper in Transactions on Audio, Speech, and Language Processing. So before I go into details, let me do maybe some brief introduction, starting what in general speaker diarization is. Speaker diarization answers the question, who spoke when? So it means that speaker diarization predicts when the segments, when the same speaker occurs. Also, it means that it is able to identify the segments when there is no speaker, so the silent segments, or the segments when there are multiple speakers, so when the speakers overlap. The standard approach to diarization is the clustered-based diarization, and its pipeline is quite simple. So firstly, we have recording. The recording is processed by voice activity detection, which task is to detect the speech segments and discard the silence ones. Then when we have this processed recording, we tag it into overlapping segments. And then from each chunk with some speaker ID model, we extract speaker embeddings. And then having these speaker embeddings for each segment, we score them, compare them between each other, and cluster them. And so having clustered these representations, we know which embeddings are in the same cluster, so which chunks are in the same cluster, so which segments are from the same speaker. The problems with that kind of approach is that firstly we have here different modules. So we optimize these modules, they are like separate, and so we optimize them separately. So the whole system is not necessarily optimized for a diarization task. And also when we have overlap, so when we have these segments, we extract from this segment speaker embeddings. We assume that in particular segments we have one speaker. So it means that when we need to deal with the segments when we have overlap, we have multiple speakers, we need some additional mechanism to deal with that. So the solution to that problems was the end-to-end neural speaker diarization systems. So EEND-NAA is just a single model that is trained directly to optimize the diarization result, and its processing pipeline is as follows. We have recording. From the recording, we extract the sequence of features. Then this sequence of feature is processed by the encoder that produces the sequence of embeddings. And the sequence of embeddings is processed by some backend. In this case, in the simplest version, it's just a linear layer. And this linear layer in general has the number of outputs equal to the number of speakers in the recording. So it means that each output corresponds to a speaker, and just returns a decision whether a speaker is present in a particular frame level embedding or not. As we can easily notice, the problem with that structure is that when we have this linear layer, we have this maximum number of speakers, the maximum number of outputs is predetermined in the network architecture. So when we want to deal with this flexible number of speakers or the number that it was not foreseen during the training, like it's not feasible to handle that. So in order to deal with that, in the backend was proposed the EDA block. It was proposed to replace this linear layer with EDA block. The EDA block is just two LSTM layers connected in encoder-decoder manner. And its task is to produce attractors. Attractors are the speaker representations. Speaker representations of the speakers that occur in the recording. So the number of the attractors in general is equal to the number of speakers that are in the recording. In theory, this EDA block can produce as many attractors as we want to. So how can we know how many attractors do we need? So this stoppage of the generation of the attractor generation is done with this linear layer that is applied on the top of this EDA block. So each of the attractors is processed by this linear layer, and task of this layer is to detect whether attractor is speaker or not. And when it detects that the particular attractor is not a speaker one, then the attractor generation is stopped. So when we have attractors, we have as many attractors as speakers. We have embeddings which corresponds to the each frame. We just do a dot product of these two, process it with sigmoid function, and we have a diarization decision at the end. So in our work, we were focusing on this backend part. So moving to our proposal, our proposal was to replace this EDA block with NAA block, where this NAA block is just built of two operations. Firstly, it's k-means clustering, which is applied on top of all frame level embeddings, where the number of clusters is equal to the number of speakers in the recording, and then refinement of these cluster centers with a transformer decoder block. Why we wanted to do it? We wanted to make the attractor generation more explainable, and at the same time use this cluster-like information from the frame level embeddings. And as it will be shown on the later slides, in general, these frame level embeddings from the encoder, they tend to generate clusters. And I mean that the frame level embeddings that belong to the same speaker, that belong to the silence, they tend to be close to each other. So we wanted also to exploit that feature. So now I will move to some preliminary results. But before I do that, I wanted to mention a few details on the experimental evaluation setup. So firstly, the data set. On the next slides, I will focus only on two speaker recordings. And the training data was mainly based on the simulated mixtures. And the mixtures were generated with the recordings from switchboard datasets and NIST SRE. As a representation of the real data, we selected a Colholm corpus, in this case, the two-speaker subset of the Colholm corpus. Input features were used Mel filter bank coefficients, and as evaluation metric was used the diarization error rate, which is a standard metric for diarization. In general, the lower value, the better. Diarization error rate is just the sum of three types of errors. False alarm, so false alarm means an error when system detects silence as a speech. Missed is an error when the system detects speech as a silence, and speaker confusion when assigns segments to a wrong speaker, and divided by a total duration of time. So when we look at the results, here is the table, and so maybe I will firstly describe the table. So here we have two models. The first one is EDA, which is a baseline, and the second one is NAA, which is the proposed one. we have 4 columns of test sets. The 3 of them are the simulated mixtures with different speech overlap. And the 4th one is the call home is the representation of real data sets. So in general, how we can observe the proposed system, it presents pretty good results. Unfortunately, it's not as low as the baseline, but we can deal it with mechanism that I will present on the next slide, which is an iterative refinement. So the problem with the first attempt of this system was the usage of the k-means. As when we applied k-means, we applied it on top of all of the embeddings. So it means when we use for clustering all of the embeddings, so also the silence embeddings, not only the speech ones. Also, the problem is when we have embeddings that belong to the overlap. So in general, the question is like when we have embedding that represent overlap, what we should do with such an embedding. Probably the best option would to use that kind of embedding to compute the cluster centers for all speakers that this embedding contain. But it's not feasible because we have a clustering algorithm, so it assigns one embedding to one cluster. So the solution to that was to apply iterative refinement of the centers. So it means when we have the first pass of the all information through the model, and having this first prediction of the diarization system was to use these predictions to compute once again these cluster centers. So in that way, we could not use the embeddings that are not speech ones and include overlap embeddings in computation of the centers that in all speakers that the particular overlap embedding belongs to. So when we look at the results, we can see like the table is the same as before. We have a new row where this new row is just an AA system with iterative refinement. And as we can observe, when we apply this refinement, we have better results comparing to our previous version of the system, but also improvement over the baseline. So the next, also I have here. So here I wanted also to show how this iterative refinement sometimes can impact the diarization decision results. So here we have a TC plot of the frame level embeddings. The labels are the diarization system decisions. In general, here we have 2 speaker recordings, so we can have 4 classes of the labels, speaker 1, speaker 2, both speakers, so it means overlap, and no speaker silence. So as we can see in this first prediction, the system decided that most of the embeddings are silent, the rest of them are mostly overlap, and a few of them is either speaker 1 or speaker 2. When we refine the centers, we can see that one of these, let's say, cloud of the embeddings was assigned to only one of the speaker. Some overlap embeddings has been changed to silent ones, and we have some little more of the embeddings from the second speaker. And when we try to refine the centers again, we can see that the diarization decision has been changed in that way that some silence has been kept. There is another speaker one, the same like as in the previous iteration, and the one decision to one, let's say, cluster or cloud has been changed to another speaker, and overlap has been kept. And we can see, like with this next iteration, the system decision hasn't been changed much. It converged and is the final one. But we can see how this decision has been changed from the iteration 1 to 4, where in the beginning we had mostly silence and overlap, and in the end we could distinguish the single speaker embeddings from overlap and silence. So now let's move to the results, to the condition when we don't have like the two-speaker recording, but when we have multiple speakers in the recording. So we can have different number. So here are the preliminary results of the system for the recordings from 1 to 4 speakers. So here in the columns, these names indicates the test sets for the recordings that contain from 1 to 4 speakers. In the rows, there's EDA system and NAA with iterative refinement. Yeah.
So how many times do you, how many cases you have with one speaker, simulated one speaker, how many times you have?
Yeah, so these are like the test set of simulated mixtures, and in each mixtures, like we have 500 utterances per each condition. Yeah. So, and these models were trained in the similar way as for two-speaker condition. So in general, what I want to show here is that for this flexible, like variable number of speakers condition, the system also achieves pretty good results. However, the problem with that system is that we have this k-means operation, and we assumed in the beginning that we apply this number of clusters equal to the number of speakers. And it also means that we need to know in advance this number of speakers, number of clusters. So it means that this system is not applicable for scenario when we don't know this number. So in order to deal with that, we are working on and proposed 3 variants of this system modified to the condition when we can handle this oracle scenario, non-oracle scenario. So in all 3 modifications, from all 3 variants, we applied similar modifications. The first one was the usage of k-means. So in general, the k-means not necessarily is used to generate cluster centers as many as number of speakers, because we don't know this number. We use k-means and generate the number of clusters with the number that is higher than the maximum number of speakers that we assume that can be in the recording. The next thing, which is quite crucial, is applying a single speaker activity detection block. It's a block that detects the embeddings that contain only one speaker and filter out the embeddings that contain silence or overlap. As here, I have some example t-SNE plots for 2 and 4 speaker recording. In general, I want to show you that on the left, we have embedding t-SNE of all embeddings. A single speaker ones, overlap, silence. On the right, we have t-SNE when we have filtered out this silence and overlap. And as we can see, when we only keep these single speaker ones, they are quite discriminative between each other, so we can use that for our work. So, and the last thing is to change decoders from 1 decoder to 2 decoders. So going to the first system, which is EEND-NAA over rest. So how this backend processing pipeline works. Firstly, we have embeddings, and we filter these embeddings with SSID. Then, having these filtered embeddings, we apply k-means. And as I mentioned here, we use k-means with the number of centers higher than the number of speakers that we think that would be in the recording. Then we, having these centers, we refine them with the first decoder block, which task is to refine the centers in such a way that we have only single representations per each speaker. And these centers, refined centers, are just processed with linear layer. that assess whether the particular center is speaker or not. And having these selected centers, they are processed by the second decoder block, producing the final attractors. When it comes to the results, the test cases, test sets are the same as in the table that I have shown before. The only difference is that we have here a result for the new system, and also we have two tables. The top one is the table for the condition when we know the number of speakers, so for the oracle condition, and the bottom one is for non-oracle condition when we estimate the speaker number. So in general, we can see that this new system, it achieves quite good results comparing to the baseline. However, it performs somewhat worse than the original NAA, but still, at least with this system, we are able to predict the number of speakers. Going to the second version of that variant of that NAA system is the EEND-NAA with two-step clustering, two-step clustering because we have clustering twice in this pipeline. So how it works? So we have frame level embeddings. We process them with SSAD block, filter out the overlap and the silence ones. Then again, we apply k-means operation with a number of centers higher than the number of speakers. And again, refine them with the decoder block. The difference between this and previous system is that the task of this decoder is slightly different. As here, we assume that when we have this higher number of cluster centers than the number of speakers, we assume that the one speaker can be represented by more than one cluster center. So in general, the task of this decoder block is to make these centers closer to each other, the centers from the same speaker closer to each other, and the centers from different speakers farther away to each other. So in that way, we can apply the second clustering, which merges these representations and providing one representation per one speaker. And when we merge them, we apply them to the second decoder, refine and obtain the final attractors. In general, during training, we use k-means. During inference, we use spectral clustering, and with spectral clustering, we estimate the speaker number. So when it comes to the results, they present as follows. So firstly, we can see that this newer system, it improves over the previous over S version. Also, what is good now, in almost all cases, these two-step results are comparable to the original NAA model. And what is also important, it performs much better than the baseline. So the last variant is the simplified version of the two-step clustering called one-step clustering, because now we only have one clustering in the pipeline. And here is it's very simple. So again, we have SSAD, we apply k-means, and this k-means now not necessarily overestimates the number of clusters. It either during training, we just used k-means with the number equal to the number of speakers, or when we need to estimate the speaker number, we apply in the inference spectral clustering. And with that, with the frame level embeddings, we estimate the speaker number. And then we use the obtain cluster centers to process them with the decoders. And when it comes to results, we can see that for oracle condition, this one-step results in most cases are comparable. When it comes to estimated condition, one step performs worse than two-step, probably because when we apply this filtering with SSAD block, this SSAD block is like it's not perfect, so it can it may not filter out, let's say, everything that it should. So probably it can provide some contamination, and that affects the estimation. But still, also this system performs pretty well comparing to baseline. And now I have the last slide with the result, just to show the results on the real data sets. So firstly, I have here Colholm. Colholm is a common benchmark for diarization. In general, what I wanted to mention here before I will show the full results on this data set. In general, Colholm test set, this subset of this data set, it has 250 utterances. However, mostly these utterances are for 2 and 3 speaker. When we look at the recordings with 4 speakers, 5 speakers, 6 speakers, there's only a few. So in general, when I will use, let's say, some statements to the results, I will mainly have in mind the results for the 2-3 subset, or the results on the whole set. So here are the tables for all the systems on the Colholm set. Here this mentioned test set. In general, what I wanted to say here, that on the real data set, the results, I would say, are confirmed. The performance in general is better than baseline. Maybe with the worst performing data set is over-S, well, not data set, like system is over-S. But in general, when we compare it to the original EDA, we can obtain some improvements. And the last results, I have here a small table for a diehard set. Diehard is a data set that is that was used in a diehard challenge. It contains recordings from different domains. In general, these recordings, they contain between 1 to 9 speakers. And also in the table here, I included a Jacquard error rate. The Jacquard error rate is another common metric for diarization systems. And it is computed in that way that when we have each ground truth speaker, for each ground truth speaker and the system hypothesis for that speaker, you compute full alarm, error, and miss, and divided by total, where total is a union of the ground truth speech and predicted speech. And the final Jacquard error rate is the average. I can, but honestly, in general, I just followed what other people doing, how they evaluate their systems. Yeah. Yeah. So yeah, but in general here, also we were able to have better diarization error rate and Jacquard error rate values when we compare to the baseline. Here, for simplicity, I have only results for NAA with this iterative refinement and NAA two-step. So that in general, that was everything what I wanted to present today. So what I presented and described was our proposal of non-autoregressive method. I presented original version of it and also the whole development and improvements to that method, including adding the feature of counting the speaker number. And also I shared with you the performance on the simulated mixtures, and real data sets. So that's it. And are there any questions?
Yeah. On that.
So each ground truth is compared, like each speaker ground truth is compared with the system high hypothesis, and false alarm is an error when system predicts silence as speech, enemies when the speech is classified as silence.
She's asking for the Gemini, right?
Yes. Yeah. Yeah, per speaker. Yeah, per speaker, and is divided by the union of the speech segments from ground truth and hypothesis.
So I have multiple questions. So do you have any control over how you're mixing the speakers in the mixtures? So how much is the overlap?
So yes, more or less. So what we are using is this this mixture this script for mixture generation that was used in original Hitachi recipe. So there is this control is done with the parameter called beta, and this beta in general it controls how much speech overlap in it is. To be more specific, it also controls how much silence we have between utterances of the utterances of the speaker between each other. Yeah.
But did you control that in some way so that you can see how it affects the performance of your system?
So I had it like, you mean in other words, the performance of the system for different speech overlap?
Yeah.
So we had it for these experiments that are for two. Yeah. So the best analysis that we have was with these two speaker recordings, where we have different speech overlap. But I feel, yeah, like to be honest, so there was also one problem here, because we control the silence, we control the speech overlap, but the problem was, but we didn't solve it that much yet. Like at least, like there are different generators of the mixtures. But what I wanted to say that we also noticed that when we have these two test sets, so in general, these three test sets are the benchmarks, kind of like this is like something what people the setup that people use to present in their papers on the simulated mixtures, but definitely, like I would say, like what we noticed that this two test set, for example, has much less silence than this test set. I think I had a table in some of our old papers. In general, I think that was the reason that sometimes we observed in the system that when we have this low overlap condition, we have, like, for example, higher diarization error rate than the condition when we have more overlap.
Also interesting to see the breakdown for not only for the results but for the other results. the false alarm pieces and
Mhm.
the confusion, just to have the statistics there and see when it gets more.
Mhm. Yeah.
Also, it's just a curiosity. So for DIPAR, you know that we have like 10 different data sets, right? So I think that the most difficult ones could be like the YouTube and the restaurant. Probably, I don't know, the children was left out for the last one. But probably those two, YouTube and restaurant. But did you observe the same, or were you able to improve on those very, very noisy and hard scenarios?
Honestly, I didn't look into this different subset. I only was observing the result for the whole data set.
Yes, it's interesting because perhaps one of these scenarios is just very bad for some reason. That's what happened to us when we were like exploring a little bit of high. One scenario is super, super bad, but it's not the YouTube or the restaurant.
Mhm.
It was another thing that for some artifacts it was not getting good results.
Oh,
So yeah.
okay. I'll look to that.